Our second talk today will be given by Foling Zou about the stability of the Lode construction.
Okay, thanks for the introduction. It's my pleasure to talk here. So today I'll report on our project in the women topology collaboration. So these are my collaborators, Alice, Sarah, Ayelet, and Birgit. And I had a wonderful experience in this women topology workshop. And I highly recommend every women topologist in the audience to go if you have a chance. Okay, so here is the plan of my talk. So first I will give an introduction about what is the Lode construction and what is the stability question. And then I will talk about some stability results and followed by instability results. Okay. So this is the definition. Here X is a simplicial set and K is a commutative ring and A is a commutative K algebra. So K can also be a commutative differential graded K algebra in the definition. And there is also the topological variant where K is a commutative ring spectrum and A is a commutative K algebra spectrum. And the Lode construction written as Lxa over the ring K is a simplicial commutative K algebra. And at nth level, we have tensors of A's over K indexed by the cells, the n cells, or the set X of n. And the phase maps and the degeneracy maps in this simplicial object is induced by those of X. So if two points in Xn gets mapped to the same point in Xn-1 by a phase map, we multiply their labels. And in the other direction, if we have a degenerate cell, we just insert a unit in the degeneracy map. So if we use the standard simplicial model of S1, we just get the cyclic bar construction. Okay, we can also put coefficients in. So we need X to be now a base simplicial set, and the coefficient is an A module, and we just, in the Lode construction with coefficients, we just insert the coefficient m at the slot indexed by the base point. And it's also alternatively the Lode construction tensor over A with m. And in this talk, we will drop the K whenever there is no ambiguity. And also in the algebraic context, we also use the Lode construction to denote the commutative differential graded algebra instead of the simplicial object. And in the topological context, we also use this to denote its geometric realization, which is a commutative algebra instead of a commutative algebra spectrum instead of a simplicial commutative algebra spectrum. Okay, so some examples when the simplicial set is S1, the Lode construction in the algebraic context is the Hochschild homology of A. And when X is Sn, this is the higher order Hochschild homology of A. This is studied first by Pirashvili, who also named this construction Lode construction. And in the topological context, this is THH of R, and the ring spectrum here is over S. Okay, so alternatively, we could think of this definition in this other way. So we can write this as A tensor X or A to the power of X, depending on which notation you use. So in the first notation, we use the fact that commutative algebra or E-infinity algebra is tensored over spaces, and this is the tensor of the commutative algebra over space. And in the second notation, we are thinking of this construction as the left adjoint in the following adjoint pair of functors. So A tensor A to the power of X is left adjoint to map out of A. And we will use this adjunction later in our proof. All right, so the question about stability is this question. is first raised by Dundas and Tanti in their paper. It asks for which pairs K and A, so K is the ring and A is the K algebra. We fix a pair and we ask for which pairs we have this implication that if suspension of X is weakly equivalent to suspension of Y, we always get their low-day construction is equivalent. So here, this equivalence is just an abstract equivalence. It's not induced by a map from X to Y. Right. So one may ask, why do we ask this question? Do we expect this to be true? The answer is no, we don't expect this to be true in general. And then here comes the question, why do we ask it? So I think, first of all, this is for fun, because we think that the low-day construction is some sort of homology theory, and we will wonder, does the suspension isomorphism in ordinary homology theory hold here, or does something similar to that hold? And more precisely, we can make this analogy precise if we had used the sum of the spectrum instead of the smash product or the tensor of the spectrum. Then we would just get the homology. So there is a way to modify the low-day construction such that we do get homology. And also, there are actually known cases of stability, and in those cases, it will help us in calculations because we have one more tool to use. Right, so here are some names of people who have studied things related to this topic. And these are two groups. This is a previous women topology group whose work, when I quote it later, I will just abbreviate using BLPRZ. Okay, so here is a remark. When K is a field, we have this equivalence that HR tensor HR over HK is equivalent to H of the tensor. So in that case, the Ellenberg-MacLean spectrum functor sends the algebraic low-day construction to the topological one. Okay, so are there any questions at this point?
As always, you can feel free to interrupt, or you can also post questions in the chat, and I'll try to monitor those and pass them along to Foling.
Sure, thank you. All right, so now I will talk about the stability results. So here is the property of stability that we mentioned earlier. And in the paper of Dundas and Tanti, they show that if A is a smooth algebra over K, then this pair is stable. So KT, the polynomial ring of K over one generator T, is an example of a smooth algebra. It's actually a free algebra, and they show this by first showing it on the free things. Okay, and here is another case where we know stability. If K is a field and A is a commutative half algebra over K, then we know then the pair is stable. So this is done in a paper by Barist, Remedus, and Young, and they proved this using representation homology, so some kind of functor homology. And in their proof, the role of the commutative half algebra structure is not so apparent, or like it's not very apparent why we have the stability in this case. So in our joint work, we give another proof of this result, which improves it slightly. So we work in the topological context and in the infinity category of spectra. So, and our algebra A here, we wrote as H. It's a commutative half algebra spectrum, which I will define later. And we have that in this case, if suspension X is equivalent to suspension Y, then the low-day construction is equivalent over X. Okay, so why are we working in the infinity category? for this theorem. This is because comonoid objects are rare in known model categories of spectra. So this is a theorem in Perex and Shipley that any strict co-algebra in symmetric spectra or orthogonal spectra or EKMN spectra is co-commutative. So if we ask the co-algebra structure to be strict, we have also asked that it has to be co-commutative. So alternatively, we work in the infinity categories and we define a commutative Hopf algebra spectrum to be a co-grouped object in commutative algebra. So we are asking the algebra structure to be E infinity and the co-algebra structure to be only E1. And some examples of this are here. If we have a topological abelian group and we do suspension of it, we get a commutative Hopf algebra spectrum because the suspension functor is strong symmetry monoidal. And if we have a pair of, if we have a Hopf algebra like above, and A is flat as a K module, then H of A is a Hopf algebra spectrum over H of K. So in theory, a commutative Hopf algebra spectrum is more general than these two examples, which the stability results for both of them are known. So our theorem in theory is more general than these known results, but actually we could not find an example of a commutative Hopf algebra spectrum that does not fall in these two categories, and it would be nice if we have that example. Okay, so I will explain the proof very briefly here. So our goal is to show that in that case, the Lode construction on X is equivalent to the Lode construction on Y. And to show that, it suffices to show that the representable functors are equivalent. And here, if we take Hom of Lode to B, using the adjunction, we get this is equivalent to Hom from X to the maps of commutative algebra from H to B. And using the E1 co-group structure on H, we get an E1 group structure on maps out of it. So this second slot is an E1 group object in spaces. And we take, so by the free and forgetful adjunction, we can replace the first space by the free E1 group object on it, which is given by loop suspension of X plus. And here, this slot, suspension of X plus only depends on suspension of X. So if we have suspension X equivalent to suspension of Y, then we will get equivalence of functors at this stage, which gives equivalence of functors from the beginning. So here in our proof, the structure of the commutative Hopf algebra is used explicitly in this step. And we can also generalize this to E2 groups and twofold suspensions with no pain. So this is for the stability result. Now I will switch my flavor to instability results. So how would someone prove that something like this is not true? They will just come up with examples of X and Y which satisfies this, and then they compute the right-hand side, they show that these are not equivalent. So the flavor of this part is very different than the previous one. We will be doing a lot of computations with the right-hand side. So our test spaces for X and Y will be the torus and the cells of it. And we know that if we suspend the product of spaces, we get something that's equivalent to suspension of X veg Y veg X mesh Y. So if we suspend the torus, which is the product of n copies of S1, we get that is equivalent to the suspension of the cells of Tn, which can be explicitly written as a veg of these spheres. So C is a wedge of spheres that gives the cells of STM. And in the paper of Dundas and Henty, where they raised this question of stability, they also showed that Qt mod T square is not stable. And they showed this by computing the Lode construction of this algebra over the torus and over its cells. And they showed that in homological dimension 2, the dimension homological degree 2, the dimension on the left is short by 1 than the dimension on the right. And in our joint work, we extend this to the case of Qt mod T to the n for all n greater or equal to 2. And we show this by computing that at homological degree m, the Lode construction on Tn is less than, the dimension of that is less than the dimension on the right, on the nth homology or homotopy of the Lode construction. And here we used reduced coefficients, while in the definition we did not have reduced coefficients. And the reduced coefficients is easier to compute. So let me introduce the tools used in this computation. So we have said that when the space is S1, then we simply get the cyclic bar complex out of the Lode construction, and we can use that explicitly to compute these objects. And in the previous Riemann topology paper, they showed that the Lode construction on spheres over Qt of the algebra Qt mod T to the n with reduced coefficients can be computed as a commutative DGA. This is quasi-isomorphic to the free symmetric algebra on two generators, one of degree m and one of degree m plus 1. And the free symmetric algebra on an odd degree generator means the exterior algebra, and on even degree generators means the polynomial algebra. And what is strange on the right-hand side is that it actually does not depend on n. So it does not depend on the power of the truncation here. So we will use this as an input. And in their paper, they computed the Lode on the two torus in low degrees using something like a cyclic bar complex or bicyclic bar complex. So this is how it goes. We can think of T2 as the product of S1 and S1. And then we can identify the Lode construction on T2 with this iterative Lode construction. And here on the right-hand side, there are two S1s. So we can think of this as a bisimplicial object, and the left-hand side as a diagonal of this bisimplicial object. But if we compute the bichain complex associated to this bisimplicial object, we can compute that in low degrees. So in this bichain complex, by degree m and n, elements or a basis of elements look like the matrices m plus 1 rows and m plus 1 columns. And this lot over the base point is an element in the coefficient field K. And all these other slots are elements in the ring A. And we have horizontal and vertical differentials, and the total chain complex of this will help. The homology of that will give us the homotopy of the Lode construction in the torus. So this is total degree 0, total degree 1, and total degree 2. Okay, so here is the claim. The Lode construction on T2 of this two truncated algebra at pi2 has dimension 3. And the basis is given by these three classes, which sit in these three slots correspondingly. And a highlight of this fact is that this class 1T T0, which sits in degree 1, 1, and it's homologous to this class. This class is a boundary, so it's not one part of the basis. And the reason for that, we can find it by a quick computation of the boundary of this class. So if we take boundary of this class, we multiply the first two columns, and then we multiply these two columns, and then we multiply the last one and the first one. So we get these three classes. And then this middle one is 0 because t squared is 0. It's an object in Q, it's an element of in Qt mod t squared, which is 0. So we get twice this class is a boundary. And since we are over Q, so this is a boundary, and it's not, thus it's not a basis in the homology. And recall that before we have quoted the result of this on the spheres, so we know that Lode on this is the free symmetric algebra generated by these elements of these degrees. So the name are like given to them randomly by me. It's not a standard name. And we can see from this basis that at pi2 we have 4 classes: x, s prime, y, y prime, and a. So the dimension of these cells at pi2 is 4. Thus, we have actually proved that modulo this claim that pi2, the Lode construction is not stable because it doesn't agree on T2 and S1 veg S1 veg S2. Okay, so we can think about this computational result in this other way. There is a spectral sequence called Greene spectral sequence, and it's about push-outs of commutative algebras, and I have adapted it into for the purpose of our Lode construction. If we have a co-fiber sequence of spaces x into y and then to y quotient x, X is a connected space and A is a commutative K algebra, then there is a multiplicative spectral sequence with E2 page pi star of the Lode on Y quotient X tensor pi star of the Lode on X converging to pi star of the Lode on the total space Y here. And here we also use reduced coefficients because in that case, without the reduced coefficients, this could also be true, but in this case, the flatness condition is easier to be satisfied. And we applied this Greene spectral sequence to this cofiber sequence S1 veg S1 included into T2, whose quotient is S2. Then we see that at the E2 page, we just get the Lode construction on this wedge of spheres, which is the cell for T2. So for the stability to hold, there have to be no differential in the Greene spectral sequence because we want the E2 and the E infinity to be identical. And if there were a differential, the dimension will not work. So what Duns and Tanti have shown is that there is actually a D3 differential in this Greene spectral sequence. And this is the only differential, and they can thus compute, at least additively, all the homotopy groups of the Lode on T2 of this algebra Qt mod T squared. Okay, so we want to extend this, and we ask this question: what about Qt mod T to the third? If we try to use this bar complex, we see that there is no contradiction in pi2, and also the number of bases grow exponentially because now at each slot you have, instead of 1t, you have 1t and t squared. So there are a lot of bases to test, and this is not very easy to compute. Well, it's very tedious. So we use this new idea that we resolve the algebra. So we think of Qt mod T to the n as the push out in this of these algebras. Qt sending T to the n and maps Qt to Qt, and vertically t sends to 0. Then this push out of algebra gives us a push out of the Lode construction for any space X. And we are going to plug in two spaces X. One is the torus and one is the cell for it. And this horizontal map will depend on the space, and we denote it by F1 and F2 respectively. So this is a push out of commutative algebras, which is also a push out of spectrum. So we can have a Tor spectral sequence. For both cases, we get Tor of, so we have Tor, we have a spectral sequence whose E2 term is Tor of these two, pi star of these two over pi star of this, converging to pi star of this thing. And I will later on explain what this A star is, but A star is just, so let me show you here. A star is just a name for pi star of these two things, and they agree for Tn and C because Qt is smooth. So we know because Qt is a free algebra, it's smooth, so we know this Lode construction agrees with Lode construction on the cells of Tn, and we call this A star. And F102 is this horizontal map but they are different. And we write that here to denote the difference of the A star module structure on this A star depending on the space. And since C is a wedge of spheres, we know everything about it. So in particular, we know F1, which is this map from A star to A star factors through the augmentation. So in the E2 of the Tor spectral sequence for C, we know we can pull this A star out of the Tor because F1 factors through Q. So we get this E2 is isomorphic to this term. And then we know the result, and we know this E2 page, we see that they are isomorphic. So we know that there has to be no differential here in this case for the Tor spectral sequence of C. So here, we can see this, find this E2 page to be Tor of QQ tensor A, and we also know that this is an isomorphism. Okay, so what about the case of the torus? So here is the ingredient to tell us lead us to the discrepancy in the E2 page. So here is a lemma. F2 maps an element in degree n, which is higher than 0, to a non-zero element in degree n. Okay, so what are these classes? Here we are computing Lode on the n torus, and we can use the n chain complex notation analogous to the bi-chain complex notation before. And in this notation, X is the class in degree n, so it's in total degree n, but n degree m n, and it's represented by a 2 times 2 times 2 matrix. And in this matrix, X has T at the slot coordinate 1, 1, 1, 1, 1, and has 1 in all other slots. So this is a cube, which is the case when n is 3. And F2 of X will be this class because F2 sends T to the m. And this class is homologous to n factorial times this other class, where now we put T's at the slots that's adjacent to the base point and 1 at everywhere else. So this is the class W. And this class also has the name n factorial times these generators in the first Hartree homology, but it's not relevant for the proof. And this is analogous with this previous fact. So previously, when we computed this class was a boundary, we find that this class 111 squared is homologous to this, and we said that t squared was 0, so this is 0. And here, this class, this one is the higher dimensional analog of this one, and this one is the higher dimensional analog of this one. And we are no longer 0 here because now we are in Qt instead of Qt mod t to the n. Okay, so the upshot here is that we have this F2 sending x to W, which is non-zero. Right, and now we can compare these E2 pages. So on the E2 page, using the previous lemma, we get this E2 for Tn has a smaller dimension than it for C. So it has less or equal to, it has a dimension smaller or equal to, we can show that easily. But what about the less? So here, this is a less. This is the degree toward 0 m. So it is the tensor, and then it's at internal degree n. And this is the class 1 tensor W, where W is F2 of x. And this class 1 tensor W, because we are tensor over A star, we can move this x to the left, and we get the augmentation of x here. And since x is in degree greater than 0, this class is 0. So this class was non-zero in above, but it becomes 0 below. So we get that E2 page here is less in dimension than the previous one. And we also know it was an isomorphism above, so that we get this has to be less than the dimension on top. And therefore, there could not be an isomorphism between them. So this proves our theorem. Okay. All right, so let me give a summary of the results I just explained. So we proved that Qt mod t to the n is not stable, and it actually works to prove that whenever n factorial is invertible in the field K, this is not stable. And we can also use this to prove when this is not a field, but the integer z, zt mod t to the n over z, this pair is not stable because low-day construction commutes with localization. And if these were stable, we would get a contradiction. But on the other hand, if the field is F2, we know F2 adjoint T mod T square over F2 is stable. This is because we can identify this truncated polynomial to this group ring of C2, and group ring of C2 is a half algebra over F2. So we know that this is stable because it's a half algebra pair. So there is some mysterious thing happening relating the characteristic of the field to the power of the truncation there. And we know this from calculational results or from proofs, but there's I don't understand why this power is so tricky here in this pair of being stable or not. So I don't think I have a good understanding of these results. And we are also interested in these other cases. What about if we have a power greater than the characteristic of the field, or if we have a power that the characteristic of the field divides, but it's not just a power of it. And we do not know the answer in these cases. Right, so that's all for my talk, and I think I finished too early. Thank you for your attention.
Okay, if you'd like to unmute yourselves, we can thank her. And we have time for questions if people have them.
Hey, Foling. So do you have a guess for what happens when you're not using reduced coefficients for the low day construction? Do you think the instability results will still hold then?
So if we know with reduced coefficient, it's unstable, then we know without reduced coefficient, it's also unstable.
Ah, cool. Okay.
Yeah.
Awesome. Thanks.
Other questions?
All right. I guess I'll ask another one. So, what conditions do you have on the Hopf algebras in Spectra that you know stability for?
I think as long as it's a commutative Hopf algebra spectrum, then it's stable over S.
Okay. Okay. So, do you know it for things like Spanier-Whitehead duals of compact Lie groups, for example?
Sorry, are those, I'm not very familiar with that. Are those commutative Hopf algebras?
I mean, so I don't know exactly what a commutative Hopf algebra in Spectra is, or like how it differs from what my intuition for it is. But like, okay, so a compact Lie group, because it's compact and it has a multiplication, then its dual should have a co-multiplication. And also the Spanier-Whitehead dual of any space is already a commutative ring spectrum. And so I don't know if that interacts well enough to make it a Hopf algebra in Spectra, but I think it's like one of the things that should be at least like a good co-algebra in Spectra.
Yeah, that's a good candidate of examples. I'll think about that. Thanks.
Cool, thanks.
Other questions?
I have a question. So in the cases where it's not stable, do you know what it's like? Have you thought about like what its stable approximation is? Like in terms of like, I guess, Goodwillie calculus of functors is like a way to approach this.
I have not thought about it, sorry, but I think that's a good question. So yeah.
The other thing I was curious was, I mean, I was gonna say like, was it conjectured that that it's always going to be not stable when your ring is like singular. But then at the end, you have this example that I guess that's not the case, right? Because there's sort of two reasons why it could vanish. Either like it's divisible, either like n factorial is 0 in your ring, or HH1 is trivial, right? If I understood your proof correctly.
Yeah, I think I understand the first reason, but why is it, I don't think HH1 is trivial is relevant here.
Well, I guess the smooth case, it vanishes. I mean, in the smooth case, you know, HH1 will vanish, and so then the obstruction would vanish. But
yeah, that's I see.
But so yeah, I was gonna guess, well, maybe it's just whenever you're not smooth, it's not going to be stable. But it seems like that's not quite what's going on. So I don't know what to make of that either.
Yeah. Yeah.
More questions? Okay, if not, then we will wrap things up here.